Welcome friends to this new video on differentiation for the 12th class students of Maharashtra State Board. Today we shall learn the rule for derivative of inverse functions. Friends, you must be remembering that in 11th standard we have already studied the rule for derivative of a sum, difference, product and quotient. Those four rules have been studied in 11th standard. And in this year, in 12th standard, we have already completed the rule for derivative of a composite function, which is called chain rule also. This is the second rule, which is rule for derivative of inverse function, and then there will be third rule, which is rule for derivative of a parametric function. So today's discussion is on rule for derivative of inverse function. See, besides the examples on this topic, the theory part is very crucial, very important. You have to prepare these proofs carefully, the rules of derivative of a composite function, that for inverse function, and one more for parametric functions. These three rules you have to prepare very well for the exam. So be careful while even thinking about the statement of such rules. So let us see the statement first. Rule for derivative of inverse function. Read it alongside me. The statement says if y is equal to fx is a differentiable function of x on an interval I, and y is 1 to 1 and on to, and dy by dx not equal to 0 on I. Also, if f inverse y is differentiable on f of I, then d by dy of f inverse y is equal to 1 upon f dash x, or in other terms dx by dy is 1 upon dy by dx, provided dy by dx is not equal to 0. Now this statement, if you look at it, it's a little bit lengthy kind of a statement. So look at the first part. First part is the condition part from here to here, and then you have the result part. So in the first part, which is the conditions mentioned here, first line says if y equal to fx is a differentiable function of x. That means dy by dx exists. Then another thing is the function y is equal to fx is 1, 1 and on to, which means that its inverse f inverse y exists. The third condition says dy by dx is not equal to 0. dy by dx is not equal to 0. Which is written because in the end you can see this expression 1 upon dy by dx. If it has to be written and it has to have a meaning, your dy by dx should be 0. And then also written here is f inverse y is differentiable on f of I. That means it's in the derivative of f inverse y with respect to y, which means d by dy of f inverse y exists. So finally what are you saying here is then d by dy of f inverse y means d by dy of what is f inverse y? Like I said earlier, whenever you write y equal to fx, if its inverse exists, it is written as x is equal to f inverse y. So x is equal to f inverse y. This f inverse y is nothing but x. So how do you read this? D by dy of x, which is dx by dy. See it here, dx by dy is equal to 1 upon f dash x. What is f dash x? F dash x is y is equal to fx, so f dash x is derivative of y, which is dy by dx, and where dy by dx is not equal to 0 is mentioned. So if the four conditions y equal to fx is differentiable function of x, that means dy by dx exists, y is 1, 1 and on to, that means f inverse y exists, and next is dy by dx not equal to 0, and f inverse y is differentiable on I, then d by dy of f inverse y is 1 upon f dash x, or dx by dy is 1 upon dy by dx. So this is the statement. Now we shall see the proof. Let delta x be a small increment in x, then correspondingly there will be increment delta y in y. We have already stated that y is a differentiable function of x. Therefore, whenever there is a small change delta x in x, there will be some change delta y in y. That's what we have written here. So as delta x tends to 0, delta y will also tend to 0. This is our first equation. We shall use it later. If you take the delta x increment very small, means tending to 0, the corresponding increment delta y in y will also tend to 0. Also in the statement, if you see, there is a line written as y is a differentiable function of x. What is written there? Y is a differentiable function of x. It means that dy by dx exists. Dy by dx sometimes we write as limit delta y by delta x as delta x tends to 0. So this line means y is a differentiable function of x, means dy by dx, which is written like this, exists and finite. Exists and it is finite. We shall take this as number 2, statement number 2. We shall use it later on. Now we shall use one simple step. We know that we have delta y by delta x into delta x by delta y. What is this product equal to? Delta y by delta x into delta x by delta y is easily written as 1. I can even write that as delta x by delta y is 1 upon delta y by delta x. Taking delta y by delta x on the other side. Now we shall take a limit delta x tending to 0 on both sides. So in the next line I shall write limit delta x tending to 0 on both sides so we have taken limit delta x. So limit of numerator means limit of 1 is just 1, and limit of denominator, which is limit of delta by delta x, is written here. Now we shall use this part number 2. What is it written there? Limit delta by delta x as delta x tending to 0 is dy by dx, and that exists. So this is dy by dx, and we have written in the condition that dy by dx not equal to 0. So we shall write here dy by dx in the next step. So this limit delta by delta x as delta x tends to 0 is dy by dx, as written here in number 2. It's to 0. So we shall replace this delta x tending to 0, this condition, by delta y tending to 0, and we may write that as limit delta y tends to 0 of delta x by delta y is equal to 1 upon dy by dx. 1 upon dy by dx. So this delta y tending to 0 is taken from 1, where we have mentioned that whenever delta x tends to 0, delta y tends to 0. Now look at this right hand side. If dy by dx is not equal to 0, then the RHS, let us take this as number 3, RHS of 3 exists and it's finite. Therefore, the LHS of 3 exists and is finite. So when RHS of 3 exists and finite means that LHS of 3 exists and is finite. And look at the LHS of 3. LHS of 3 is this: limit delta x by delta y tends to 0. If we say it exists and it's finite, it is written as dx by dy. So this dx by dy exists. Therefore, limit delta x by delta y as delta y tends to 0 exists, and it is finite. At the same time, it is equal to dx by dy. We can mention this also in the same step. Exists and is finite. Therefore, we shall take this dx by dy in number 3, and we shall get dx by dy from 3, and let us take this as number 4. So from 3 and 4, what do we get? Dx by dy is equal to 1 upon dy by dx, provided dy by dx is not equal to 0. This has been mentioned in the condition itself. So we can prove this like this, hence the proof. So we have proved the rule for derivative of inverse functions, and that needs some practice. So let us see some examples. The first example is written here: find derivative of y, this is y or this is y in first and second example. Find derivative of y with respect to x using the derivative of its inverse function, x equal to f inverse y. So original function is y equal to f of x. Its inverse function x is equal to f inverse y has to be found, and using its derivative, means derivative of x, that means dx by dy. Using dx by dy, we have to find derivative of y, which is dy by dx. So we have to find dy by dx using dx by dy. So let us start with the first example. Here we have y is equal to cube root of x plus 4. So what we shall do is, we shall find x from this expression, and that is done by taking cubes on both sides. So taking cubes, I get y cube is equal to x plus 4. Then I want x, so take 4 on the other side. So y cube minus 4 is equal to x. That means x is equal to, whenever you write y is equal to f of x, it means that x is equal to f inverse of y. So x means f inverse y is equal to, what is x? Means f inverse y is equal to y cube minus 4. So we have found the inverse function x is equal to f inverse y here. X is equal to f inverse y in general, x is equal to f inverse y, but in particular x is equal to y cube minus 4 in this example. So we shall use this x is equal to y cube minus 4, x is equal to y cube minus 4, and we shall find out dx by dy. So we have to differentiate this with respect to y. I mentioned that differentiating with respect to y, what I get is differentiating with respect to y means d by dy of x, that is dx by dy, is equal to d by dy of the right hand side, which is y cube minus 4. Which means dx by dy is equal to, now d by dy of y cube minus 4, it's just like d by dx of x cube minus 4. What do you write that? D by dy of y cube minus 4 is same as d by dx of x cube minus 4. You write x cube derivative is 3x square. In the same way, y cube derivative is 3y square with respect to y. So there is no need of multiplying this expression by any other thing. So d by dy of y cube is 3y square minus d by dy of 4 is 0. Constant's derivative is 0. So d by dy of right hand side is written. Dx by dy is 3y square. So it means that dy by dx, which we shall find by using the rule which was proved just before some time, dy by dx equal to 1 upon dx by dy. See, that rule can be used like this. Earlier, if you remember, the rule was stated as dx by dy is 1 upon dy by dx, and here we are using dy by dx as 1 upon dx by dy. One and the same thing. You can use it in this manner also. So dy by dx is equal to 1 upon dx by dy, which is equal to 1 upon, what is your dx by dy you have found? It is 3y square. Now we normally finish the answer in terms of x. So what is 3y square? How do you write 3y square in terms of x? So look at this y. This was your y. So replace this y by cube root of x plus 4, and it will give you 1 upon 3 into what is y? Cube root of x plus 4 and then y square. So this is your answer. Dy by dx is equal to 1 upon 3 into cube root x plus 4 whole square. You can even write this as cube root of x plus 4 bracket square also. This 2 can be written inside also. Or you can write this as x plus 4 raised to 2 by 3. 3 into x plus 4 raised to 2 by 3. That is also okay. We shall stop at some stage like this. What we did in this example was, we took y as it is, then we found x from that y's expression. So for that we have to find x on one side. So make necessary arrangements and write x in terms of y, then differentiate that x with respect to y and get dx by dy. And after getting dx by dy, use the rule dy by dx equal to 1 upon dx by dy. So use that dx by dy in that step, and then finish the answer in terms of x. So take y, write x, find derivative dx by dy, use rule dy by dx is 1 upon dx by dy, and finally write the expression in terms of x. Here are the steps. Let us solve this one more example of this type. See this, y is equal to log of 2x minus 1. So as in the previous example also we did, we write x in terms of y from this expression. So for that, what should we do here? This is y is equal to log of 2x minus 1. So you mean that the base is not mentioned, means e. Now convert this expression in exponential form as e raised to y is equal to 2x minus 1. That's how we do it. Logarithmic expression converted into exponential expression in this manner. So e raised to y is equal to 2x minus 1. Now we can find this 2x equal to e raised to y plus 1, taking 1 on the other side. Again this 2 not required, so x is equal to e raised to y plus 1 upon 2. So we have written x in terms of y. This is our inverse function. X is equal to f inverse y, which we required is e raised to y plus 1 upon 2. This is x, which is f inverse y, which they have asked you to find, and then differentiate this x with respect to y to get dx by dy. So let us do that step. X is equal to e raised to y plus 1 upon 2 written here, then differentiating with respect to y because we want to find out dx by dy. So 1 upon 2 is done by first of all taking 1 upon 2 constant outside, then d by dy of what is remaining inside, e raised to y plus 1. Now 1 by 2 as it is, and then d by dy of e raised to y plus 1 is same as d by dx of e raised to x plus 1. How do you write d by dx of e raised to x plus 1? D by dx of e raised to x plus 1 is just e raised to x plus 1's derivative 0, just e raised to x. So d by dy of e raised to y will be just e raised to y plus derivative of y with derivative of 1 with respect to y is 0. Constant's derivative is 0. So just that much. So it is e raised to y upon 2. And finally, like I said, dx by dy is written. So we can write dy by dx from it. So dy by dx is equal to, using the rule dy by dx is 1 upon dx by dy, writing dx by dy in it, and then you write 1 upon e raised to y upon 2 means what? 2 upon e raised to y. Finally, this dy by dx has to be written in terms of variable x. So get rid of this e raised to y, get rid of actually this y, and that has to be done by using the original definition here. So this e raised to y itself is written here 2x minus 1. So replace this e raised to y by 2x minus 1. So answer will be dy by dx is equal to 2 upon, what is e raised to y? 2x minus 1. So dy by dx is 2 upon 2x minus 1. That's how we can answer these questions. And make sure that the proof of the earlier statement which we proved today, rule for derivative of inverse function, that statement should be that proof should be prepared very well, because that can be asked in the exam. And these some examples, 1 or 2 examples we have seen here, which will be helpful to understand the rule. The basic form is 1 upon dy by dx is 1 upon dx by dy, or dx by dy is 1 upon dy by dx. So remember this and solve the examples.